Hi guys, how you doing? It's Mr. Gagnon. Again, these videos are best presented at 1.25 speed. Google tends to slow down my voice. So, this section here is it's kind of nice because it's a little review of period and frequency. But we're actually talking about now is something called simple harmonic motion. And if you go to Webster's definition of harmonic motion, they give you a definition that says it's a periodic motion, as of a sounding of a violin string or a swinging pendulum that has a single frequency or amplitude or is composed of two or more such periodic motions. So I'm going to take that definition and I'm going to simplify it for you guys a little bit. Now, when we talked about something called uniform circular motion, we talked about a circle like this, and I don't know if you recall, but this object that swung around the circle here completes one cycle. Okay, we say that's the period, the time it takes to go around one cycle. So as we go around this circle, it's considered to be one cycle. Well, other things have this type of motion. One thing that I can think of is a swinging object. So if I have an object that swings up like this, it ends up here, okay, and then it swings back and ends up here. So this is going to be a swinging object. It goes, if I let it go from here, it goes this way and this way and this way and this way. And in a perfect world, this would swing forever. But we know that we do have existing forces on the object. So this is something that has a periodic motion. Another thing that has a periodic motion would be, I'm going to do my best to draw a picture of this. Okay, this is a side view of a speaker. This could be a speaker that's in your car. Okay, and if you were to look at a side view of that, this would be a big magnet on the back side. And this is called a diaphragm, and this diaphragm vibrates back and forth. So it'll actually go back and forth and vibrate at a certain frequency to produce sound waves. So this might vibrate up to, and I'll try to do my best here, but it might vibrate up to this point at its max point, then vibrate back down to this point at its min point. So at rest it's sitting here, but then we send electricity through the magnet and it actually shakes this diaphragm and moves it up and down. Okay, this would be a periodic motion as well. One more example would be if I had let's say a frictionless surface here, and I've got a spring attached to a mass that's on the ground here, and I pull this thing back and I let it go. Okay, it's going to stretch out maybe to here. Okay, that's the max point, and then it might shrink. When I let it go, it's going to go back this way, and right back here might be the min point. So if I let this go, it's going to go back and forth, right? Especially if we take away friction here, and air friction, that'll just go back and forth forever in a periodic motion. So we can think of periodic motion as something that happens over and over and over and over and over again. And yes, you can apply that to a lot of different things. So, reading directly from the notes, there's a deep connection between simple harmonic motion and uniform circular motion. Simple harmonic motion can be thought of as a one-dimensional projection of uniform circular motion. You remember when we learned all about uniform circular motion? We can apply this to simple harmonic motion. So this first part's going to be a quick review. Okay, and I'll let you guys take some notes if you want to. If you already know this from the past, you don't have to. But we have something called a period. Okay, and we said that this was the time it takes for an object to complete one circular path around another object here. So the time it takes to complete one path, okay, as a period. And this definition is extended to, let's say, a situation like this where we're swinging something back and forth. Okay, the time that it takes to get back to the start point. So let's say I let go here, it swings out to here, then swings back to here. Okay, the period is the time it takes for it to go this way and this way. Okay, so the period is the time it takes for it to go all the way out here and all the way back here. Okay? And similarly, in our picture of the speaker, okay, I'm going to be a little bit, make it a little easier. Here's our magnet. Okay, with our speaker, okay, it's one period would be the time it takes for the diaphragm here to go up to its high point and then back to its low point. So one period is the time it takes for it to complete one cycle back to its original state. So if I started the speaker up here, it would have to end up back here. So one full like up and down. So one full up and down with the speaker would be the period of that object. And again, if we have a spring, the block on it, okay, and the block, we'll say the block is touching the ground, and we stretch that out to, let's say, here. Okay, the period is the time it takes for this to come back to here once I let go. So if I pull this and I let this thing go, it's going to go this way and back this way. So this way and this way is considered to be the period of motion of that. And if we remember from past, I'll write it down for you. The period is equivalent to the time over the number of, we'll call it oscillations. So an oscillation would be like here to here. An oscillation would be from here to here. An oscillation would be from here to here. So this is the time, and these are the number of oscillations. Forgive my spelling there. So that's the case. So as with period, okay, we have another term called frequency, and that is 1 over the period. And frequency can be looked at in terms of like how often it happens. So I'd like to look at the speaker example, okay, for you guys, and relate it to sound and the frequency of sound. So just to give you a very simple definition here, okay, so the human ear can pick up sounds all the way down to about 20 hertz, which means that this speaker has to go up and down and repeat its cycle 20 times per second. So 20 times, so this thing has to go up and down 20 times really fast per second in order for us to actually hear it. In our range, and I'm going to give you a cool applet to listen to in the next section. But the range is between 20 hertz and 20,000 hertz. So that means that our ears can hear a speaker that goes all the way from the low of 20 times per second, really low sound, all the way up to a frequency of about 20,000 times per second. And that would be a very high-pitched sound. I'll give you a pretty cool applet to look at later, and you can kind of see the difference. But yes, that means the actual speaker here is going up and down 20,000 times in a second. That's why really big speakers like subwoofers cannot reach that frequency, because they're actually too big to do that. Okay, we can't vibrate a surface that big. Let's say you have a 12-inch subwoofer in your car. You can't vibrate that surface that fast. It's actually impossible. But if you have a tiny little speaker, and we call those tweeters, a little tiny speaker with a very tiny surface on it, you can get that to vibrate at a frequency of 20,000 hertz or more. So this video is getting long-winded, so I'm going to leave you off there, and I'm actually going to we'll shut it down for now, and we'll move on to the next section. We'll be taking a look at velocity and its relationship to all this.